Hi everyone, I'm Jeremy Arsenal, and I'll be presenting the data science team's insights and modeling results from our most recent assignment of analyzing loyalty customers and predicting spend for potential customers. Let's jump into the agenda. So the data team's task was to analyze 15,000 of our loyalty customers with two main objectives. One was to gather spending habits and insights from our current loyalty customers. Second was to then use this data to build a predictive data model that can predict household spend for prospective households. And today I'll be walking you through the data used in the modeling process, some characteristics around BBY's loyalty customers, how we selected our final model, and the results from the final model. The data team was provided with in-house customer loyalty data across 15,000 profiles. We were also provided with some supplemental data tables to provide enrichment to the in-house data. This additional data included consumer data regarding consumer purchasing habits, household donation data giving each household's donation history, magazine subscription history, and each household's political leanings. Once all data was combined, we had 79 different variables at our disposal for model input, although we did not use all variables for a variety of reasons. Our first reason was that many variables included a lot of blank, unknown, null, and NA values, which collectively we will refer to as missing data. We removed all variables that had at least a 29% missing data rate, as we felt anything above this threshold would not aid in model performance. This resulted in 51 variables being eliminated. Included in the chart above are the 25 variables with the greatest missing data. And through our process, we discovered that the provided data contained a large amount of noise, which made analysis tricky and difficult to find meaningful trends and correlations between customer personas and variables. And with that in mind, we still think our model can provide some insights to the company, and we will continue to seek out more data for further enrichment of our in-house data to try to find stronger signals and insights. Now moving on to our data sampling and enrichment techniques. The data originally contained 3 sections. Training data contained 15,000 household profiles, testing data contained about 5,000 profiles, and the prospective listing had about 6,000 profiles. For model development purposes, we used 10% of the training data for the V-treat process that aided in our data feature engineering. This left us with 13,500 household profiles to train our models. Once the models were trained, we then tested their performance on the remaining 5,000 profiles within the testing set to ensure the models remained relatively stable and did not have any performance or overfitting concerns. As part of the data exploration process, our team looked at some key characteristics of current loyalty customers. We found that customer spending had a relatively normal distribution, with average spend per household at about $300 and the median spend at about $315. We also looked at how frequently customers visit BBY stores and found that almost 70% of them visited at least 6 times in a given 12-month period, with almost a quarter of customers visiting 8 times in a 12-month period. Continuing with more current customer insights, we found that customer ages were evenly distributed across an age range of 30 to 90 years old, with the average and median age being 63 years old. We also thought customer wealth might be important to consider for future spending habits, so that the team looked at the distribution of customer home values and found that the median home value was around $190,000. But given the randomness provided in our data, there was no discernible effect of home ownership on spending. However, our team will revisit this once we obtain more data that is not as randomized. After looking at characteristics of all of the provided BBY loyalty customers, our team carved out a subgroup of high spenders. These spenders were customers that were designated as spending above the 3rd quartile of all spending, which was anything over $365. We found that there were no perceptible differences in characteristics between high spenders and regular customers. For instance, age and store visit frequency were almost identical to the full sample of customers. We further looked at education, location, home value, and a few other variables and noted that they were all very similar to the full sample of customers. Moving on to our modeling process. Before finalizing our model, we trained and tested 4 different algorithms: gradient boosting machine, a linear regression, random forest, and XGBoost. Given the inherent randomness in the data, we believe that experimenting with these varied algorithms would maximize our chances of finding the best model fit. As mentioned earlier, the performance of all models was not particularly strong, which we attribute to significant noise in the data, which also reduced its signal strength. To improve performance, we plan to seek additional data sources for enrichment. From the results displayed, all models demonstrated comparable outcomes across accuracy metrics. However, the XGBoost model performed slightly better than the others, with a mean absolute error of 63, mean absolute percentage error of about 40%, and a root mean square error of 85. In terms of model fit, XGBoost achieved the highest R-squared value of approximately 25%. While this is not as strong of a result as we'd like to see, it is a noticeable improvement over the other models. After training our models, we applied them to a test data set of 5,000 instances to ensure model stability and confirm that the models were not overfitted. As shown in the results, the XGBoost model continued to outperform the other 3 models. While the root mean square error increased slightly from 85 to 90, this change was within an acceptable range, and we were confident that the model was performing as expected without overfitting concerns. Other metrics remained stable, with the mean absolute error increasing marginally from 63 to 68, and the mean absolute percentage error rising slightly from 42% to 43%. Given the model stability and its marginally better performance metrics, we selected the XGBoost model for predicting prospective household spending. This slide presents the predicted household spend distribution based on the XGBoost model. The median predicted household spend is $300,000, while the average is around $296,000. While these values align closely with historical household spending data, it's important to acknowledge that this model is not performing significantly better than simply using the average as a baseline prediction. The relatively high noise in the data and the modest performance metrics of the model suggest that it captures some patterns, but lacks the ability to make highly precise predictions. As you can see over here to the right, the distribution shows a sharp peak around $300, indicating that most households fall near this value. However, the model's tendency to cluster predictions near the average reflects its limited ability to differentiate more nuanced spending behaviors. While the results provide a reasonable starting point, future improvements, such as acquiring cleaner or more relevant data, will be critical for achieving more accurate and actionable predictions. To conclude, our team identified several high-level characteristics of our loyalty customers, despite facing significant challenges with the available data. We observed that our customers are evenly distributed across age groups and exhibit spending habits that follow a normal distribution. We trained 4 different models to enhance prediction capabilities, with the XGBoost model emerging as the best performer. While the model's predictions align with general spending patterns of loyalty customers, it's important to note that its performance may not be much better than using the average as a baseline. The model lacks nuanced differentiation on a per customer basis due to the data limitations. Moving forward, our team will focus on acquiring additional data and refining our approach to achieve more precise and actionable results. Thank you for your time and attention, and I'm happy to address any questions you may have.